Well, I'm back after a long hiatus. We're going to do something a little different this time. We're going to tackle the Basel problem. Now, the Basel problem, not this Basel, it's a different Basel. The Basel problem is a mathematical conundrum that was first posed in 1650, and it was outstanding for not quite a century. Okay, so I guess we're dealing in the mathematical community like medium hard crossword puzzle. It was solved by Euler, the mathematician Euler, in 1734, and made him kind of famous because it's a difficult problem. It's a difficult problem. So we're going to, well, my plan is to investigate this problem uh, using a technique different than the one that Euler used. There are some pretty good videos which deal with not only Euler's technique. There's one by there's one by Mathologer, and I'll link that, as well as there's a really good visual by 3 1 Blue Brown, 3 Blue 1 Brown, him. So check out their channels, check out their videos on the Basel problem. The approach that we're going to take here is one by the mathematician Cauchy, who is known for his horrid theory of limits. But what what the plan is here is to make this proof accessible to anyone who knows their high school algebra. So if you've got your high school algebra, your high school pre-calculus, then you're going to own this problem at the end of however many videos this takes. So that's the goal. So we're going to focus on just this one problem and do a bunch of maths. So let's look at what the problem is. All right, and there it is behind me. The Basel problem. It's spelled Basel, not Il, like the plant, or like Basil. You know that faulty towers. No, this is a different Basel. And spoiler alert. There's a solution right there. So somehow, all of this sequence, we've got a, can you see it okay? We've got an infinite sequence. It goes on forever. There's the dots. Okay, goes on forever. And really, it's the sum of the reciprocals of the squares of the positive integers. Okay, so it's a series. It's a sum of a series. It's an infinite series. So it's 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, etc., etc., etc. This, it's not even immediately obvious that it converges to anything, okay? Because, I mean, it might not. Yeah, it might creep on up forever. It does start to slow down eventually, but sometimes these things look like they're going to end up someplace. And who'd have thought that it would have ended up at this pi squared divided by 6? Okay, so there's the solution. Okay, so if you're the sort of person that likes to look in the back of the book and you got the answer, now move on to the next, that's fine, you're done. Okay, but if you want to see how we can squeeze pi squared by 6 out of this infinite sum, then stick around. In this video, we're just going to describe the problem. Okay, then we will go step by step through several videos. That's the plan anyway. We'll see how far we get. Okay, the plan is to go step by step through several videos, cover a bunch of different kinds of mathematics that will lead us finally to this lovely beast. One other thing, before we finish this, we will have a look at this. It's what you call sigma notation, and really, it's a shorthand way of describing a sum like this. Okay, and you might have seen it before. We'll go over that. So let's take a look. See now at we'll take a look at this sum and some of the partial sums that it goes up to. So here we are. So here, for reference, we've got at the top of this, table, we've got pi squared divided by 6, and it equals 1.644, et cetera, et cetera, et cetera. Okay. Now, the first 10 terms of this infinite sum, the first 10 terms, it comes out to 1.549, etc. I'm reading it backwards, so it's a little bit difficult. Okay, so it doesn't look like it's in a real hurry to get to this pi squared by 6. So you can see that if you were to add up a bunch of these, it's 1650, and you're going to add up a bunch of these. I don't know that you would guess pi anything. Okay, look at this. After 100 terms, there, we've got 1.634. I mean, oh, great. So now we're down to 2 terms, and it falls apart after the third term, the second term after the decimal point. After 1,000 terms, so now we've added up 1,000 of these terms that we've generated, and what do we got? 1.643. Okay, so now we've got 3 terms, and that 3, I guess if we rounded it, yeah, we could argue that we're pretty close to 4 terms. Okay, that's after 1,000. So this sum isn't really in a hurry to go anywhere. On a side note, if you're going to work on this, you're going to need some coffee or some tea or something like that. Like, I don't, what is this? I hear about people like doing mathematics without a drink of coffee or tea. Like, I don't get that. Is that a thing? I don't know. So, like, don't try that. Like, no, seriously. I mean, you know what? You need you got to be slurping on something yummy in order to do this. I mean, because you know what? We're going to be here for a little while. Right. So let's take a look. We're gonna graph this. We're gonna graph this and just have another look at how it converges. Okay, so there we go. Now, one thing I want to point out here is that we've got the down here at the bottom, we've got the number of terms. Where is it? Okay, you can't really see my hand, it disappears. Okay, we've got the number of terms, okay, increasing to only about 25. Okay, so we're only going up to about 25. Okay, and I'm using a different scale. Okay, I'm using a different scale for the horizontal and the vertical axes. So I want you to be aware of that. Okay, so I'm not trying to pull one over on you here. But we've got a red line up here on the top. Okay, that red line that's pi squared divided by 6. Okay, so that's what we're saying that the function gets to, this infinite sum. And now you can see we're dealing with it's not smooth, okay, because we're dealing with values, partial sums calculated at various integers. Okay, so for 1 term, or then for 2 terms, and for 3 terms. So the horizontal axis down here, where the horizontal axis down here, okay, that tells me how many terms we're looking at. Okay, so as we increase the number of terms, I mean, we can see it does seem to shoot up there pretty quickly, and then it meanders and takes its time, but it seems to be getting closer and closer to that pi squared by 6 line. So, it does seem feasible, but for all we know, after a million terms, it's going to cross it. Okay, so it seems like it could be asymptotic, which I'm approaching it forever and ever, but not quite getting there, but getting closer. How do we show this algebraically? That's what we're going to start in the next video. We're going to begin with that. But before we finish off here, one note about this sigma notation, because we're going to be using that a fair bit, and it's just a compact way of describing a series. Okay, so we're going to take a look at that. Okay, and so here we go. Okay, so it's behind me. At least it's what it looks like on the graphic. Okay, so what we've got is, now if you understand the idea of a series, a bunch of terms, one after the other, and there's some sort of rule for generating them. Okay, so the first term follows, we describe the first term, and then the second term is created by following some rule, like multiplying by something or adding something. All right, so what we've got here is the recipe for creating that series. So the sigma is there. It's just telling us, hey, we're going to sum up a series. That's all it is. It's a Greek letter, capital S, basically. It looks like an E. It's a sigma. It's an S, and underneath that, we start with n equals 1. So that just says we're going to start with term number 1. Okay, we're numbering the terms. Okay, so these are the indexes, the indices of the term. And in this case, we're going up to 5. Okay, so we're going to go from the first, second, third, all the way up to the 5th term. So in this case, it's only a partial sum. And that 5 is, so that 5 is on the top of the sigma. And then we've got the general rule that we're going to follow. I mean, so in this case, it's just n. Okay, so what we've got here is 1 plus 2 plus 3 plus 4 plus 5. That's all we've got. We'll show some other examples. Actually, I'll do that right away. We're going to show some other examples to make some sense out of this. Hang on. All right, so you'll see just above my head there, there's one example where, so the general term is 3n plus 1, and we're just doing 3 terms. So we've got a partial sum from n equals 1 to 3. And so you see, just following that, we've got 3 terms where we've replaced n with 1, then 2, then 3. And then we sum that up, and we end up with 27. Now, underneath that, notice how we've got the n in a different spot, and we've started with 0 because we can start with anywhere. And so we go 0, 1, 2, 3, 4. So we're going to have 5 terms, and so 2 to the power of n is the general term. So the first term is going to be 2 to the power of 0, then 2 to the power of 1, then 2 to the power of 2 and 3 and 4, and then that all adds up to 31. Okay, so I mean, you're going to get used to this. So that's it for now. Please remember to like, comment, share, and all that stuff, and join me next time when we are going to begin our arsenal of mathematical tools in order to tackle this problem, and we'll begin with looking at proof by induction. So that's next time. So we'll see you then, or well, we won't. I won't, but you'll see me, I guess. Thanks. Bye.